The sunlight on your skin is 8 minutes old, and on a bad day, riding inside that ordinary light is a burst of X-rays from an explosion that has already happened. You are seeing the warning and the event in the same instant. By the end of this video, you will understand how a knot of magnetism becomes a flash brighter than a billion bombs, why the truly dangerous part of a flare arrives hours behind the light, and how thin the margin is that lets us prepare for it. We orbit an ordinary star. It hangs at the center of the solar system, a glowing sphere of gas, and from where we stand it looks like the steadiest thing in the sky, a fixed lamp that pours out warmth and light with what seems like perfect constancy, unchanging from one morning to the next. That impression is an illusion produced by distance. The sun is not solid, and it is not calm. It is a ball of plasma, gas heated until its atoms have been torn apart into bare nuclei and free electrons, so that the entire body becomes electrically alive, threaded through with magnetic fields that bend and coil and, every so often, snap. The light that feels so even on your face is the surface of something deeply restless. You cannot see that restlessness with your eyes, and that is the first thing worth understanding. In ordinary visible light, the sun gives almost nothing away. It is simply too bright. Even a major eruption barely lifts its apparent glare. But aim an instrument at it that is tuned to ultraviolet or to X-rays, wavelengths our eyes were never built to register, and a different object appears. Loops of glowing plasma the height of several Earths arch off the surface and collapse back into it. Bright points flare and fade across the disk. Whole regions brighten in seconds and then dim again, as though the star were breathing in light. These sudden brightenings are solar flares, and they are among the most violent events in the solar system, even though, from here, they pass in complete silence. That silence matters, because it shapes how we misread the sun. There is no sound in space, no thunder to mark these radiant storms, no flash bright enough to catch your attention if you happen to glance up. A flare can release, in a handful of minutes, more energy than our entire civilization has used across its whole history, and the sky above you will not so much as flicker. The wind does not stir. The afternoon goes on exactly as it was. Our senses are simply pointed the wrong way to register the disturbance, tuned to a narrow band of the spectrum in which the sun keeps most of its violence hidden. And yet, in the space between the sun and the earth, something enormous has been set loose, moving outward in every direction at once. It helps to be precise about what that something is, because the word explosion sends the imagination in the wrong direction. A solar flare is not a chemical fire. Nothing is burning. There is no combustion, no blast wave rolling through gas the way a shell tears through air. What erupts instead is stored magnetic tension. The surface of the sun, smooth as it looks from 150 million kilometers away, is a churning sea of charged plasma, and woven invisibly through that plasma are magnetic field lines, looping, twisting, winding around one another. When those lines become too strained, they break and reconnect into a simpler arrangement, and the energy that had been locked in their tension is dumped, all at once, into heat and light and motion. The flash that results can be brighter than a billion hydrogen bombs, and it is made not of fire but of radiation. That radiation is light, in the full meaning of the word. It spans almost the entire spectrum at once, from long, slow radio waves to searing X-rays and, in the strongest events, gamma rays. And because it is light, it travels at the only speed light can. It crosses the gulf between the sun and the earth in about 8.5 minutes, arriving on exactly the same clock as the ordinary sunshine that warms a window ledge. This is the heart of the matter, and it is worth holding on to, because everything that follows turns on it. The light from a flare comes first. It outruns everything. It outruns the solar wind, it outruns the shock fronts, and it outruns the slower, heavier, far more dangerous thing that may be following close behind. If you find these reflective explorations of the cosmos meaningful, a like or a subscribe helps us continue making them, because the sun, when it strikes, does not strike only once. The flash of light is the first blow, and on its own it is mostly a nuisance. It floods the upper atmosphere with energy, swelling the layer of charged particles high above our heads and scrambling the radio signals that pass through it. But it does little more. The second blow is the one that does the damage, and it moves on an entirely different clock. In the most violent eruptions, the sun hurls out a vast cloud of its own substance, plasma and tangled magnetic field together, billions of tons of it, flung into space behind the light. That cloud does not travel at the speed of light. It crawls, by comparison, taking anywhere from a day to several days to cross the same distance the flash covered in minutes. The light is the warning. The cloud is the event. Think of them as two messengers dispatched from the same doorway at the same instant. One is weightless and travels at the absolute speed limit of the universe. It arrives in minutes, breathless, carrying word that something has happened. The other is freighted with matter, a slow and ponderous wall of it, and will not arrive until the messenger who outran it has long since fallen quiet. They were sent together. They carry news of the same eruption, but one reaches us first by a margin so wide that, if we are paying attention, it becomes the whole difference between being caught unaware and being ready. That gap, between the seeing and the striking, is the most remarkable thing about a solar flare. By an accident of physics, the sun announces its worst behavior in advance. The instant a flare erupts, its light is already on the way to us, carrying the news. And only later, hours or days later, does the matter arrive that can knock out a power grid, blind a satellite, or sicken an astronaut. We are handed a head start we did nothing to earn. The entire effort of modern solar science, the fleet of spacecraft, the telescopes, the forecasting centers that never close, can be understood as one long attempt to make use of that head start, to read the warning in the light before the blow lands in the matter. Reading it is harder than it sounds. The light tells us that an eruption has occurred, and roughly how fierce it was, but it does not reliably tell us whether the heavy cloud is coming too, how fast it is moving, or whether it is aimed at us, or will sail harmlessly past. A flash in the X-ray band is a plain fact. Almost everything that matters about the blow behind it must be inferred, modeled, and raced against the clock. The warning, in other words, is real but incomplete, and the hours it buys are spent decoding it. It is a strange inheritance, this fragile advantage, and we have built an entire quiet apparatus around defending it. It is a head start measured in hours, and hours are not very much. A warning is only useful if you can understand what it means, and for almost all of human history we could not. We felt the consequences of solar flares long before we knew the sun was the cause. Ancient skywatchers recorded strange lights dancing near the horizon and strange disturbances in their instruments, and they reached for spirits and omens because they had nothing else to reach for. The light arrived, the warning arrived, and no one could read it. For thousands of years the sun delivered its messages faithfully, and we stood beneath them, illiterate, mistaking the auroras for the campfires of the dead or the wrath of gods, feeling the occasional shiver pass through a compass needle without the faintest notion of what had touched it. The warning system was working perfectly. The receiver had simply not yet been built. What changed was not the sun, but us. The slow accumulation of better glass, of instruments steady enough and observers patient enough to watch the same star, day after day, and notice when it did something it had never been recorded doing before. The receiver, when it finally came, was not a single machine, but a habit of careful looking, and it belonged at first to only a handful of people scattered across a few quiet observatories. One of them happened to be watching on the right morning. The story of how we learned to read it begins, surprisingly precisely, on a single morning in the middle of the 19th century, at the eyepiece of one quiet, methodical English astronomer who looked up at exactly the right moment and saw something no human being had ever knowingly seen before. On the morning of the 1st of September, 1859, in a small private observatory attached to his house at Redhill, in the county of Surrey, a 33-year-old Englishman named Richard Carrington was doing what he did on almost every clear day. He was drawing the sun. The son of a wealthy brewer, with money enough to spend his life as he pleased, Carrington had chosen to spend it on a single, patient project. He projected the sun's image through his telescope onto a screen and traced, day after day, the dark sunspots that crept across its face, building a careful record of how they moved. From that slow accumulation, he hoped to measure how the sun itself rotated. It was meticulous, unglamorous work, the kind that rewards a steady temperament. And on this particular morning, it placed him, entirely by chance, at the only eyepiece on Earth pointed at exactly the right place at exactly the right moment. A little after 11 o'clock, as he was marking the positions of a large and complicated group of sunspots, 2 points of intensely bright white light appeared within the group. They were so brilliant against the ordinary glare of the projected disk that Carrington's first thought was that something had gone wrong, that a gap had opened in his apparatus and let raw sunlight through. It had not. The lights were real, and they were on the sun. They brightened, shifted shape, drifted a short way across the spot group, and then, over the course of about 5 minutes, faded and were gone. Carrington, realizing he was watching something extraordinary, rushed to fetch a witness, but by the time he returned, the display had all but vanished. He had just become the first human being to knowingly see a solar flare, and he had no word for what it was. He was not entirely alone. A few miles away, another English amateur named Richard Hodgson, observing the same sunspot group through his own instrument, saw the same burst of light. The two men reported their observations independently to the Royal Astronomical Society, where they were read out side by side, two careful accounts of a phenomenon that had no name and no explanation. What they had witnessed was a white light flare, a flare so powerful that its brightening could be seen in ordinary visible light against the sun's already overwhelming glare, which is rare even among large flares. They had caught the sun, for the first time in recorded history, in the act. Something else happened at almost the same instant, though Carrington could only note it, not interpret it. In the Magnetic Observatory at Kew, on the western edge of London, the instruments that tracked the steady drift of the Earth's magnetic field gave a sudden, sharp jolt, a small kink in the trace, timed to the flare. The light from the eruption had crossed the gulf to Earth in its 8.5 minutes and, on arrival, had reached down into the upper atmosphere and tugged, very slightly, at the planet's magnetism. Carrington saw the coincidence in the records and was careful, almost to a fault, about what he made of it. He would not claim that the flash on the sun had caused the twitch at Kew. "One swallow," he wrote, "does not make a summer." He recorded what he had seen, set it beside what the instruments had measured, and left the connection as an open question. The warning had been received. He was too honest a man to pretend he could yet read it. And then the waiting began, though no one knew they were waiting. The flash was over in 5 minutes. The small magnetic jolt subsided. The 1st of September went on, and the 2nd of September dawned, and for 17 hours the Earth carried on in apparent calm. But the calm was an illusion of distance once again. The light had come and gone. The matter was still crossing. Behind the flare, the sun had hurled out an immense cloud of its own charged substance, and that cloud, far slower than the light that had announced it, was closing the distance at a speed that should have been impossible. 17 hours after Carrington set down his pencil, it arrived. What followed was the largest geomagnetic storm in recorded history. Across the night side of the planet, the sky caught fire with color. Auroras, normally the private spectacle of the far north and far south, spilled down toward the equator until they blazed over the Caribbean, over Hawaii, over Colombia, over Queensland in Australia. They were not the faint green shimmer most people picture. They were vivid curtains of crimson and white, bright enough to read a newspaper by in the middle of the night. In the Rocky Mountains, a party of gold miners is said to have risen in the small hours and begun cooking breakfast, convinced by the glow on the horizon that morning had come. People who had never in their lives seen an aurora stood in the streets of tropical cities and watched the sky burn. The beauty came with disruption, and the disruption fell, with a kind of grim precision, on the single most advanced technology of the age. The 1850s were the first decade in which human beings had strung electrical wires across whole continents. The telegraph was the nervous system of the industrial world, and the storm tore through it. Across North America and Europe, telegraph networks failed. Operators received electric shocks from their own equipment. Sparks leapt from the keys and the relays. In some offices, the sparks set the paper tape alight, and small fires broke out. Strangest of all, on some lines the operators discovered that they could disconnect their batteries entirely, and the telegraph would keep working, carrying messages on the current the storm itself was inducing in the wires. For a few hours, the aurora was running the telegraph. A burst of light from a sunspot had reached across 150 million kilometers of empty space and seized control of the most modern machine on Earth. This was the moment the abstract became concrete. For all of history before it, solar storms had spent themselves harmlessly on a planet with nothing delicate enough to register them. Now humanity had built something that could feel the blow, and the blow had landed. And yet, even with the flash and the storm both written plainly into the record, the connection between them remained, for a long time, in dispute. It seemed extravagant, almost absurd, to claim that a flicker of light on the distant sun could throw a continent's telegraph network into chaos 17 hours later. The most formidable physicist of the era, William Thomson, later Lord Kelvin, worked through the energy such an effect would require, and concluded that the sun simply could not supply it. A direct causal link, he argued, was impossible. His authority settled the question against the sun for the better part of 2 generations. Carrington's white light flare and the Great Storm of 1859 sat together in the books as a striking coincidence and nothing more. The warning had been seen and the blow had been felt, and still the two could not be joined. It took more than 100 years to prove what Carrington had been too cautious to assert. By gathering magnetometer traces from observatories around the world, by collating the historical reports of the auroras, and later by reading the chemical fingerprints that violent solar events leave behind, scientists reconstructed the 1859 event in detail. The cloud of solar matter had crossed from the sun to the Earth in roughly 17 hours, where such a cloud usually takes 2 to 4 days. That extraordinary speed could only mean one thing: an eruption so violent that it had swept the space ahead of it clear, letting what followed race through almost unimpeded. The flash Carrington saw, and the storm that broke over the telegraph were, beyond any doubt, 2 halves of a single event. The light had come first, and the matter second, exactly as it always does, and a careful observer had watched the opening act without ever knowing the second was on its way. That is why the Carrington event remains the benchmark against which every solar storm since has been measured, the worst case at the edge of the record, the standard by which we ask how bad things could possibly get. Carrington himself never grasped the full shape of what he had found. His later life was difficult and ended badly, and he gave his name to the event almost by accident, simply because he had been the one drawing the sun on the right morning. But that single act of patient looking became the 0 point of an entire science. Everything that came afterward, every instrument trained on the sun, every forecast issued, every satellite nudged into safe mode, traces back to 2 bright beads of light in a sunspot group, and a man honest enough to admit he did not understand them, to understand what he had actually seen, what those beads of white light truly were, and why a quiet star should suddenly tear itself open and fling its substance across the solar system. We have to look closer at what the sun is made of, and at the invisible architecture that had been winding tighter and tighter all through that summer, beneath the very spots that Carrington was sketching. Begin with the material itself, because everything about a flare follows from what the sun is made of. On Earth, we are used to 3 states of matter: solid, liquid, and gas. Heat a solid and it melts. Heat the liquid and it boils into vapor. But keep adding heat. Push the temperature high enough, and matter changes again, into a 4th state that is far more common in the universe than the 3 we know best. Nearly all the visible matter in the cosmos, every star that burns in the night sky, exists in this state. The solid, liquid world we live on is the rare exception, not the rule. The atoms themselves begin to come apart. Their electrons are torn loose from their nuclei, and the gas becomes a roiling mixture of charged particles, negative electrons and positive nuclei moving freely among one another. This is plasma, and the sun is made of almost nothing else. From its blazing surface to its unimaginable core, it is a single vast body of plasma, more than 1,000,000 times the volume of the Earth. What makes plasma behave so differently from ordinary gas is precisely that its particles carry electric charge. A cloud of charged particles in motion is, by definition, a flowing electric current, and electric currents generate magnetic fields, and magnetic fields in turn push and steer charged particles. Matter and magnetism, in a plasma, are no longer separate things that happen to share the same space. They are locked together. Physicists describe the field as being frozen into the plasma. Where the gas goes, the magnetic field lines are dragged along with it, and where the field is strong enough, it grips the gas and forces it to follow. It is a little like dye stirred into honey. The pattern is carried bodily by the moving fluid, and you cannot shift the one without shifting the other. This single fact, the marriage of matter and magnetism, is the source of nearly everything dramatic the sun does. A flare is, at bottom, what happens when that marriage is pushed past what it can bear. Now set this restless, magnetized body spinning, and add the detail that turns a stable star into a storm engine. The sun rotates, but it does not rotate the way a solid ball does. A cricket ball spins as one piece, every part of it completing a turn in the same time. The sun cannot do this, because it is not solid, it is fluid, and different parts of it are free to turn at different rates. Its equator sweeps around in a little under 25 days, while the regions near its poles take closer to 35 days to complete a single rotation. This unevenness is called differential rotation, And on a star threaded through with a frozen-in magnetic field, it has a relentless consequence. The faster-moving equator continually drags the field lines ahead of the slower poles, stretching them, wrapping them around the body of the sun turn after turn after turn, like thread winding ever tighter onto a spindle. The effect compounds without rest. The equator gains very nearly a full extra turn on the poles every few months, so that across a single span of activity, the field is wrapped around the sun not once or twice but many times over, growing more strained with every lap. Picture what this does over weeks and months. A magnetic field that began as something simple, running smoothly from one pole to the other, is taken hold of by the turning plasma and wound up. The lines are stretched out along the direction of rotation, pulled into long bands that circle the sun. They are squeezed together, intensified, and twisted around one another until, beneath the surface, the field has been concentrated into tight, strained ropes of magnetism. Each rope holds the energy of all that winding the way a wound spring or a twisted elastic band holds the work of the hand that turned it. The sun, simply by spinning unevenly, is loading itself like a weapon, slowly, continuously, and out of sight. The ropes do not stay buried. Magnetism, concentrated this way, makes the plasma around it lighter than its surroundings, and like anything more buoyant than the fluid it sits in, a magnetic rope rises. It floats upward through the body of the sun until it breaches the surface, arching out into a great loop and plunging back in, so that the rope pierces the visible surface in two places, where it leaves and where it returns. And here, at last, the invisible architecture becomes something we can see. For where a rope of intense magnetism breaks through the surface, it changes what that patch of the sun looks like. These are the sunspots. The surface of the sun is normally a churning carpet of hot plasma rising from below, dumping its heat into space and sinking back down, an endless boil that carries energy outward from the interior. But where a strong magnetic field punches through, it stiffens the plasma and chokes that convection off. Heat can no longer well up freely through that patch, so the patch runs cooler than everything around it, by something like 1,000 to 2,000 degrees. It is still ferociously hot, hot enough to glow. It only looks dark because it sits against a background that is hotter and brighter still. A sunspot is not a hole, and not a cold place in any ordinary sense. It is the footprint of a magnetic rope, a spot on the sun where the field can be thousands of times stronger than the magnetic field of the entire Earth, pinned to the surface for all to see. It was in the light of a sunspot, in 1908, that the American astronomer George Ellery Hale first measured a magnetic field anywhere beyond the Earth, reading its strength in the way the spot split the colors of the light it gave off, and so confirming that these dark marks were magnetic to their core. The dark marks Carrington spent his mornings tracing were the visible tell of the hidden, straining field beneath. Sunspots almost never appear alone. They come in pairs, and in sprawling groups, the two ends of the same magnetic ropes, joined above the surface by arching loops of field that we can photograph in ultraviolet light, glowing arcades standing over the spots like the ribs of some enormous cage. A region like this, with its tangle of looped and twisted field, is called an active region, and it is the cradle of the solar flare. The most complex and contorted active regions, where ropes of opposing magnetic direction are crammed against one another, and the field is strained almost to breaking, are exactly the places where the sun's pent-up energy is most likely to tear loose. The energy that powers a flare brighter than 1 billion bombs is nothing other than the energy that the turning sun spent weeks winding into that strained and crowded field. None of this runs at a constant pace. The winding and the unwinding follow a rhythm, a great magnetic heartbeat that takes about 11 years to complete. Over the first half of the cycle, the field winds up, sunspots grow more numerous, and flares come thick and fast, until the sun reaches a peak of activity called solar maximum. Then the strained field reorganizes itself. The sun's magnetic poles trade places, north becoming south and south becoming north, and activity subsides toward a quiet solar minimum before the whole process begins again, with the polarity reversed. We have watched this clock for a long time, though we learned to read it only relatively recently. In the 1830s, a German amateur named Samuel Heinrich Schwabe began observing the sun on almost every clear day, not to study its spots at all, but in the hope of catching a small, undiscovered planet crossing its face. He never found his planet. What he found instead, after 17 years of patient counting, was that the number of sunspots rose and fell on a regular rhythm of roughly a decade, the first hard evidence that the sun keeps time. The count of sunspots now stretches back over centuries, and the cycle now underway is the 25th to be formally numbered since careful records began. The sun that looks so changeless from a window ledge is in truth keeping 11-year time, breathing in spots and flares and falling quiet again, over and over, across the whole of human history. So the spot group Carrington was sketching in the late summer of 1859 was no random blemish. It was a knot of wound and crowded magnetism near the height of its cycle, its field strained close to the limit of what it could hold. Everything was in place. The spring was wound. What remained was the trigger, the single act by which all that stored magnetic tension is released in a handful of minutes. And that act, the snapping and rejoining of the field lines themselves, is the true engine at the heart of every flare. The trigger has a name, and it is one of the most important and least intuitive processes in all of physics: magnetic reconnection. To see what it means, return to the active region, that crowded knot of field where ropes of opposing magnetic direction have been forced up against one another. Recall the rule from a moment ago that in a plasma the field is frozen in, locked to the matter, so that field lines move with the gas and never simply pass through one another. That rule is what holds the strained field in place, building tension, refusing to release it. Reconnection is the breaking of that rule, and it happens in a place so thin it is almost not there at all. Where two regions of oppositely directed field are pressed together, the change from one direction to the other cannot be instantaneous. It has to happen across some layer, and the harder the fields are pushed together, the thinner that layer becomes. Squeezed down far enough, to a sheet that may be only meters or tens of meters thick within a structure spanning thousands of kilometers, the frozen-in condition finally fails. Inside that razor-thin current sheet, the field lines can no longer keep their distance. They snap, cross, and rejoin into a wholly new arrangement, abandoning the strained, stretched geometry they had been forced into and falling back into something simpler and far less energetic. Seen in cross-section, the reconnecting field traces out the shape of the letter X. Strained field drifts steadily inward from two opposite sides, meets at the center, breaks, and is flung out at high speed from the other two. The X point is the small, busy hinge on which the whole eruption turns. And all the energy that had been stored in the difference between the old shape and the new one is released at once. What that release looks like is a kind of slingshot. A field line bent into a sharp, strained corner is like a length of elastic pulled taut and pinned. The instant reconnection unpins it, it whips back toward a straighter shape, and because the field is still gripping the plasma, it hurls that plasma along with it. Out of the reconnection point, jets of solar material are flung in opposite directions at enormous speed. The plasma is heated, in the act, to tens of millions of degrees, hotter by far than the surface it came from. And in the violent electric fields of the reconnecting sheet, individual particles, electrons, and atomic nuclei alike are caught and accelerated until they are moving at a sizable fraction of the speed of light, particles that, in the largest events, will later reach the Earth as a hazard all their own. Heat, light, and fast particles, all three pour out of the same small region in the same few minutes. The flash that Carrington saw was this: the sudden glare of plasma heated and lit by field lines, snapping back into a calmer shape. The numbers are difficult to hold in the mind. A single large flare can release, in a matter of minutes, more energy than the whole of humanity generates in its power stations across many thousands of years, and it does so from a patch of the sun's surface that, against the full disk, looks small. That energy does not come from burning, and it does not come from the sun's core. It is withdrawn, all at once, from the bank of magnetic tension that differential rotation spent weeks or months depositing. The flare is the account being emptied. For a long time, reconnection looked, on paper, like the wrong answer. When physicists first calculated how quickly field lines could break and rejoin in a current sheet, the figure came back hopelessly slow, slow enough that a flare ought to take months to unfold, rather than the few minutes we observe. That early picture still carries the names of those who built it, the physicist Eugene Parker among them, and the gap between its leisurely prediction and the violence the sun actually shows became one of the central problems of the field. Reconnection plainly does run fast. Exactly how, through thin sheets that tear and fragment and churn as they break, has occupied solar physics for more than half a century and is not yet entirely settled. The strangest feature of the whole process is its sense of timing, the deep mismatch between how slowly the energy is stored and how suddenly it is spent. For days, even weeks, the field winds tighter, the active region grows more contorted, the strain climbs, and from the outside, almost nothing seems to happen. The sun looks no different from 1 hour to the next. Then, in a few minutes, sometimes in seconds, the accumulated tension of all those weeks is released. It is the behavior of a stick bent further and further by steady hands. For a long time it simply bends, storing the effort silently, giving no sign of how close it is to the edge, and then it breaks, all at once, releasing everything it held. The buildup is gradual, and in its way, visible. We can watch an active region grow more tangled and know that it is dangerous. The breaking is sudden, and the exact moment it chooses to come is one of the hardest things in solar physics to foresee, a difficulty we will have to return to. When the break comes, it leaves a signature written across the face of the sun that we have learned to read in detail. As the reconnection flings some of its plasma jets downward, they slam into the denser layers below and set them ablaze, and we see two long, brilliant ribbons of light straddling the magnetic divide, marking where the energy is being dumped into the lower atmosphere. Above the ribbons, where the field has reconnected and settled, glowing arcades of loops appear, rank upon rank of them, each loop a strand of reorganized field, now filled with hot plasma, cooling and raining back down. Photographed in ultraviolet and X-ray light, a flaring active region becomes one of the most beautiful sights in the solar system, a structure of light built in minutes on a scale that would swallow the Earth many times over. The white beads in Carrington's telescope were the crudest possible glimpse of this, the small part of the spectacle bright enough to show through in ordinary visible light. And here the engine connects directly to the thread that runs through everything. Reconnection does not only make the flash. When the snapping field is part of a larger structure that overlies the active region, the same upheaval can blow that overlying field open and fling a vast cloud of plasma off the sun entirely. The flare, the burst of light and X-rays, and the coronal mass ejection, the launched cloud of matter, are very often the two products of one reconnection event, born in the same instant. The light leaves at once and arrives in 8 minutes. The cloud is hurled off behind it and takes its day or its 3 days to cross. Two messengers, light and matter, are made together in that thin reconnecting sheet and sent out on their two different clocks. The whole structure of the warning, the thing the whole warning turns on, is forged in the single act of the field letting go. What makes reconnection more than a quirk of our own star is that the same process runs almost everywhere a magnetic field meets a plasma. It crackles continuously in the Earth's own magnetic field, on the night side of the planet, where it powers the substorms that brighten the aurora. A dedicated set of 4 spacecraft, the magnetospheric multiscale mission, was flown in tight formation through those reconnection sites for the express purpose of catching the field in the act of breaking, close to home where we could watch it directly. Flying only a handful of kilometers apart, the 4 craft sampled a reconnection region from the inside, more finely than any instrument before them, and confirmed in our own backyard the same process that lights the distant face of the sun. The same process is wrestled with in the laboratory, in the magnetic bottles that researchers use to try to confine plasma for fusion, where unwanted reconnection can spill the contents in an instant. And it operates in the magnetized atmospheres of other stars, and in environments far more extreme than anything our quiet sun can produce. Reconnection is one of the universe's basic ways of converting stored magnetic strain into heat, light, and motion, and the solar flare is simply the example unfolding closest to us, on a star near enough to study in extraordinary detail. To study it that way, though, we have to know where on the sun a flare actually lives. The light and heat of the eruption are not stamped onto a single surface, but spread through a layered atmosphere, each layer at its own temperature and its own altitude, each responding to the flare in its own way. The 2 ribbons glow in one layer, the looping arcades in another, the highest and hottest gas in a third that is stranger than all the rest. To picture a flare igniting, and to understand how its light comes to span the entire spectrum at once, we need to climb up through those layers. From the visible surface, Carrington watched to the searing, tenuous crown above it that holds one of the sun's deepest unsolved puzzles. The first thing to abandon, climbing upward, is the idea of a surface at all. The sun has nothing you could stand on, no shell, no skin in the solid sense. What we call its surface is simply the depth at which the plasma thins out enough for light to escape and fly free to our eyes. Below that depth, the gas is opaque, a fog so dense that light can travel only a short way before being absorbed and re-emitted. Above it, the gas is clear. The boundary between the two, the layer from which the sunlight on your window ledge actually departs, is called the photosphere, and it is astonishingly shallow, a bright rind, only a few hundred kilometers deep, wrapped around a body more than 1,000,000 times the Earth's volume. Everything we ordinarily mean by the sun's appearance, its roundness, its color, its blinding glare, comes from this thin skin. The photosphere glows at a temperature of about 5,500 degrees Celsius, and seen up close, it is not smooth but granular, paved with countless bright cells the size of countries, each one the top of a column of hot plasma welling up from below, spilling its heat into space, and sinking back down darkened at the edges. This is the boil described earlier, the convection that carries the sun's energy outward, frozen for an instant into a mottled golden texture. The sunspots sit embedded in this layer, the cool, dark footprints of the magnetic ropes, and it was across this surface, and no deeper, that Carrington watched his two beads of white light flare and fade, rise above the photosphere, and something strange begins, something that runs against every expectation. The next layer up is the chromosphere, a few thousand kilometers of thinner, redder gas. They're normally drowned out by the glare below, but briefly visible during a total eclipse as a narrow crimson ring around the blacked-out disk, fringed with countless small jets of plasma flung upward like blades of fiery grass. And as you climb through the chromosphere, the temperature, instead of falling, begins to rise. By the top of this layer, the gas is hotter than the surface beneath it, climbing from a few thousand degrees into the tens of thousands. You are moving away from the source of the sun's heat, its deep interior, and yet things are growing hotter, not cooler. Beyond the chromosphere lies a remarkably thin shell called the transition region, and across it the temperature does not merely rise, it leaps. Over a distance that is trivial by solar standards, the gas jumps from tens of thousands of degrees to more than 1,000,000. And then you are in the corona, the sun's outermost atmosphere, the part most people have never seen because it too is normally lost in the glare. During a total eclipse, when the moon covers the disk exactly, the corona springs into view as a vast pearly crown of soft white light, streaming outward in petals and plumes, far beyond the body of the sun itself. It reaches out for millions of kilometers, fading gradually into the wind of particles that blows from the sun across the whole solar system. And it is hotter than anything beneath it, 1 to 3 million degrees in its quiet state and far hotter still inside a flare. We know this from the light the corona itself emits. For decades, a bright green line in the eclipse spectrum defied all identification and was put down to a supposed new element, coronium, found nowhere on Earth. The truth, worked out in the 1940s, was stranger than any new element. The line came from iron atoms, stripped of many of their electrons, something that can happen only at temperatures of millions of degrees. The corona had not been hiding a new substance. It had been advertising an impossible heat, and no one had known how to read the message. This is one of the deepest puzzles in the study of the sun, and it has a plain name, the coronal heating problem. Common sense, and the ordinary physics of heat, says that as you move away from a fire, you should grow colder. Stand back from a bonfire and the warmth fades. That is simply how heat spreads. The sun's furnace is its core, unimaginably far below, and the photosphere, closest of these layers to that furnace, is indeed the coolest of them at 5,500 degrees. But then, impossibly, as you continue outward, away from all that heat, the temperature climbs by a factor of hundreds. The thin corona, perched at the very top, farthest from the fire, is the hottest layer of all. Something is pouring energy into that tenuous outer gas and depositing it there, against the natural flow of heat, and for a long time, no one could say what. The answer, as far as we can tell, is once again magnetic, which is why this puzzle belongs in a story about flares. The corona is laced through with the same looping, snapping field that produces the great eruptions, and the leading explanations both draw on it. One holds that the corona is heated by an unending storm of nanoflares, countless tiny reconnection events, each one far too small to notice on its own, but so numerous and so relentless that together they keep the outer atmosphere boiling at millions of degrees, a continuous faint crackle of the very process that, scaled up, produces a Carrington event. The other holds that magnetic waves, launched by the churning surface, travel up the field lines and break like surf in the thin upper gas, dumping their energy as heat. Most likely both play a part. Either way, the corona is not warmed by its nearness to the core, from which it is utterly cut off. It is warmed from within, by the field, and untangling exactly how is one of the questions that has sent spacecraft diving toward the sun to take its measure from the inside. With the layers laid out, the anatomy of a flare finally comes clear, because a flare is not an event in any single one of them. It is a vertical convulsion that threads them all. The reconnection happens high up, in the coronal loops, where the strained field finally breaks. From there, the freed energy races both ways. Some of it climbs outward and helps drive a cloud of plasma off the sun, but much of it plunges down the legs of the loops, beams of accelerated particles, and floods of heat pouring along the field lines into the dense chromosphere and photosphere below, where they slam to a halt. That is where the two bright ribbons blaze, in the lower atmosphere, lit by energy released far above them. And in the most violent flares, the pummeling reaches all the way down to the photosphere itself and heats it until even that deepest layer brightens in ordinary visible light. That is precisely what Carrington saw, not the reconnection itself, hidden high in the corona, but its lowest and most brutal imprint. The surface struck so hard it flared white. The energy was unleashed at the top. The visible mark of it was stamped at the bottom. It is worth pausing on where that energy does not come from, to keep the picture honest. The sun shines, year upon year, because deep in its core it fuses light elements into heavier ones, and that nuclear furnace is the ultimate source of every photon the sun has ever sent us. But a flare is not a hiccup of the core, and it does not run on fusion. Its power is drawn entirely from the magnetic tension stored in the outer layers, wound up by the turning of the star and released by reconnection. The furnace keeps the sun alight. The field is what makes it dangerous. There is one more consequence of this layered structure, and it carries us back to the thread of the warning. Because a flare lights up gas at every temperature at once, from the relatively cool struck surface to the million-degree corona above, it does not glow in a single color. Each layer, at its own temperature, radiates its own kind of light. The cooler gas gives off visible and infrared. The hotter chromosphere and corona blaze in ultraviolet. The searing, freshly reconnected plasma and the accelerated particles throw off X-rays and, in the strongest events, gamma rays. All of it leaves the sun together, in the same instant, a single flash that spans the entire electromagnetic spectrum from end to end. And all of it, every wavelength, travels at the one speed light can travel, crossing to the Earth in 8.5 minutes. To understand what that flash does when it arrives, and why it is the first and fastest half of the sun's two-part blow, we have to follow the light itself across the gulf and watch it strike the top of our own atmosphere. 8.5 minutes after the field breaks, the flash reaches us. It arrives as the same ordinary sunshine that has been falling on the Earth all along, only with a sudden surplus riding inside it, a spike of ultraviolet and X-rays that the quiet sun never sends. You feel nothing. You see nothing. No part of your body is built to register the difference, and even if it were, the air above you absorbs the dangerous wavelengths long before they reach the ground. The whole encounter takes place far over your head, in a layer of the atmosphere most people never think about, and it begins the instant the light arrives, with no interval at all between the warning and the first blow. That layer is the ionosphere. High above the weather, beyond the altitude where aircraft fly, the air is so thin and so exposed to the sun's radiation that sunlight knocks electrons loose from the atoms there, leaving a permanent, faint haze of charged particles wrapped around the whole daylit planet. This is the ionosphere, and in ordinary times, it is one of the quiet conveniences of life on Earth, because a layer of charged particles reflects radio waves. Send a shortwave radio signal up at the right angle, and the ionosphere bounces it back down, far over the horizon, letting a single transmitter reach across an ocean or a continent. For the better part of a century, long-distance radio has leaned on this invisible mirror in the sky. We knew the mirror was there before we ever saw it. When Guglielmo Marconi sent a radio signal clear across the Atlantic at the turn of the 20th century, the feat should have been impossible, for radio travels in straight lines, and the curve of the Earth stood squarely in the way. Something high overhead had to be bending the signal back down. Within a few decades, the physicist Edward Appleton had measured the height of that something by bouncing radio waves off it and timing the echo, proving the ionosphere real, and winning a Nobel Prize for reading a layer of the sky that no eye could see. When the flash from a flare arrives, it strikes that mirror and deforms it. The surge of X-rays and extreme ultraviolet pours into the upper atmosphere on the sunlit side and tears electrons loose far faster and far lower than the gentle, ordinary sunlight ever does. In particular, it floods the lowest level of the ionosphere, a region that is normally too thin to matter, and turns it abruptly into a dense, absorbing fog. And a fog is exactly the wrong thing to do to a mirror. Radio waves that would have bounced cleanly off the higher layers now have to pass through this newly thickened bottom layer first, and instead of reflecting, they are soaked up and lost. Across the entire daylit face of the Earth, shortwave radio can fade, weaken, and in the strongest flares go completely silent. This is not an abstraction. High-frequency radio is still the backbone of communication in exactly the places where nothing else reaches. Aircraft on transoceanic and polar routes, far from any ground transmitter, depending on shortwave to stay in contact with controllers. Ships in the open sea, remote settlements, emergency and military networks built to work when everything else is down. When a major flare erupts on the day side, all of them can lose their voices at once. Pilots over the Atlantic or the Pole find their radios full of static or dead and have to fall back on other procedures and reroute around the silence. The danger is sharpest when the blackout falls at the worst possible moment. In the autumn of 2017, as one of the strongest flares in more than a decade erupted, shortwave radio failed across the Caribbean at the precise hour that emergency teams were leaning on it to coordinate relief in the wake of a catastrophic hurricane. The sun does not check what is happening below before it fires. Its timing is its own, and now and then it falls cruelly. The disruption sweeps across half the planet in the time it takes the light to arrive, which is to say almost instantly, and it follows the sun. It is strongest where the sun stands directly overhead and fades toward the edges of the daylit hemisphere, leaving the night side untouched, because the night side is in shadow and the flash cannot reach it. The same thickened, disturbed ionosphere does something subtler to the signals we now depend on most. The faint timing signals from navigation satellites have to pass down through the ionosphere to reach a receiver on the ground, and when that layer is suddenly churned and over-ionized, it bends and delays those signals unpredictably, smearing the precision of satellite positioning at the very moment the radio is failing. The flash, in other words, reaches straight past our defenses and into two of the systems a modern society leans on without thinking: the airwaves and the map. In Carrington's century, the flash had almost nothing to disturb, for the wireless did not yet exist. Every decade since, we have woven more of ordinary life into exactly the part of the spectrum of flare scrambles, so that a fade in the shortwave bands now runs through aviation, shipping, and emergency response all at once. What makes the flash so distinctive, and so important to the larger story, is the one thing it does not give us: time. Every other hazard from the sun travels slower than its own announcement, which is the whole reason a warning is possible. The flash is the exception. It is made of light, and it carries its own news, and the two cannot be separated. The instrument that detects a flare detects it by catching the very X-rays that are, in that same instant, disturbing the ionosphere. There is no gap to exploit, no minutes in hand, no chance to act before it lands. We see the flare, and we feel the flare together. This is the literal truth behind the strange idea offered at the very start, that on a bad day you are watching the warning and the event arrive as one. For the flash, the warning is the event. It is a humbling kind of warning, one that cannot be acted upon in time, and for most of history, it was the only kind the sun appeared to offer. The whole value of the flash lies somewhere other than in the harm it does on arrival. And yet the flash is, in the end, the gentler half of what the sun can send. Its disruption is real, but it is shallow and brief. The radio fades, and then, as the burst of X-rays subsides over the following minutes to hours, the overcharged ionosphere relaxes, the absorbing layer thins back out, the mirror reforms, and the shortwave signals return. The flash is a slap, not a siege. Sudden, one-sided, confined to the daylit hemisphere, and over almost as quickly as it came. A flare, acting through its light alone, has never darkened a city or burned out a transformer. It scrambles communications for a while, and then lets them go. So if the flash itself is survivable, why watch for it so anxiously? Why build a global apparatus to catch each one within seconds? Because the flash is the messenger, not the message. The light is how we learn that an active region has just torn itself open in a major reconnection event. and that single fact changes everything about the hours ahead. A large flash tells the watchers that the field has broken violently, and therefore that the slower, heavier consequences of that same break may now be on their way. Storms of fast particles, and perhaps a great cloud of magnetized plasma launched off the sun behind the light. The flash is read not for what it does, but for what it foretells. The forecaster's clock does not start when the cloud is sighted or when the particles arrive. It starts the instant the X-rays spike, in the same moment the radios fade, because that spike is the first and earliest sign that the sun has done something that may be about to reach us in a far more dangerous form. This is why the flash, harmless as it largely is, sits at the very center of the warning. It is the opening line of a message whose later lines may or may not be coming, and which may or may not be addressed to us. To make any use of it, the watchers must do more than notice that a flare has happened. They must measure it, grade it, decide in the first minutes how serious it is and how much of a threat the unseen second half might pose. That demands a way of turning a flash of light into a number, a scale precise enough to separate the daily flickers of an active sun from the rare eruptions that could put a continent in the dark. Building and reading that scale, learning to take the measure of a flare from the X-rays it throws across 150 million kilometers of space, was the first thing the watchers had to master before the warning could be made to mean anything at all. The first thing to understand about measuring a flare is that you do not do it by eye. Carrington's white beads were a fluke, the rare case of a flare so violent that its lowest imprint showed through in visible light. The overwhelming majority of flares leave the sun's ordinary appearance untouched. To take the true measure of an eruption, you have to watch the part of its light that tracks the released energy most faithfully, and that part is X-rays. A flare announces its real strength not in the glare we can see, but in a flood of X-rays we cannot. And so the instruments that grade flares are tuned to listen on that channel, watching the sun's X-ray output and nothing else. For decades now, that watch has been kept from geostationary orbit by a line of American weather satellites, known by the abbreviation GOES. They are best known for the cloud images on the evening forecast, but alongside the cameras pointed down at the Earth, each one carries a small sensor pointed the other way, at the sun, measuring the strength of its X-rays in a narrow band, second by second, day and night, year after year. The result is one of the most valuable continuous records in all of space science, an unbroken trace of the sun's X-ray brightness, a line that ticks along quietly at a low level for days and then, when an active region lets go, leaps upward in a sudden spike before sliding back down. That spike is a flare, caught and measured in real time, its size written immediately into a number. The number follows a scale that is worth knowing, because it is the language in which solar storms are first reported. Flares are sorted into 5 classes, labeled from weakest to strongest: A, B, C, M, and X. The crucial feature of this ladder is that each rung is 10 times the one below it. A B-class flare is 10 times as strong in X-rays as an A C is 10 times a B, an M is 10 times a C, and an X is 10 times an M. Within each class, a further number gives the fine detail, so that the brightness climbs smoothly through the decade before the letter changes. Because the steps multiply rather than add, the distances involved are enormous and easy to underestimate. An X-class flare is not modestly stronger than an M. It is 10 times stronger and 100 times stronger than a C. The letters compress a range so vast that the smallest and the largest flares differ in power by many thousandfold. To feel the spread, picture a faint A-class flare as a single candle. On the same multiplying ladder, an X-class flare is a searchlight, and the very largest flares ever seen are brighter again by as much over that. The eye would call them all simply bright. The X-ray trace tells them apart by factors of thousands. In practice, the lower rungs of the ladder are the sun, simply breathing. A and B flares occur constantly, all but unnoticed. Class flares are common and usually harmless. It is at M class that effects begin to bite. The brief polar radio fades and minor disturbances. And it is the X-class flares, the rare top of the scale, that produce the planet-wide dayside blackouts, the radiation worth taking seriously, and, often though not always, the great launched clouds of matter. When a forecaster sees the X-ray trace vault into X territory, the first alerts go out within minutes, before anything but the light has arrived, warning that shortwave radio is about to fade across the sunlit half of the world. For the people who must act on them, these classes are translated into a planar, public scale of radio blackout levels, running from minor to extreme so that an airline dispatcher or a coast guard need not follow the physics to know that the bands are about to go quiet. The letter and the number are for the scientists. The alert is for everyone who depends on the sky staying usable. This way of grading flares, by raw energy rather than by appearance, was itself something we had to learn. In the decades before satellites watched the sun in X-rays, flares were ranked by how they looked through a telescope filtered to the red light of hydrogen, sorted by their apparent size and brightness into a rough scale of importance. Observers at a network of ground stations watched the sun through hydrogen filters and logged each flare by hand, calling it minor or great by how much of the disk it lit, a judgment that leaned as much on the steadiness of the watcher as on the flare itself. It was the best that could be done from the ground, and it measured the wrong thing, how impressive a flare looked, rather than how much energy it had truly released. The move to X-ray classification was a move from the surface to the substance, from how loud a flare seemed to how much force was actually behind it. Learning to read the sun's voice meant, in the end, learning which frequency to listen on. Every so often the sun says something the instrument cannot fully hear. On a day at the very start of November in 2003, near the end of a stretch of ferocious activity that space weather forecasters still call the Halloween storms, an active region near the edge of the sun unleashed a flare so intense that it overwhelmed the GOES X-ray sensor outright. The detector climbed, reached the top of its range, and pinned there, unable to register anything higher, like a set of scales pressed past their maximum. The flare went on growing while the instrument built to measure it sat saturated and blind at its ceiling. The true size had to be reconstructed afterward, from the way the saturation behaved and from the depth of the disturbance the flare carved into the ionosphere, and the reconstruction placed it at around 28 on the X scale. By some estimates higher still, the most powerful flare ever directly recorded. It did not come alone. The Halloween storms were a fortnight of fury, a single giant active region firing off one major flare after another as it crossed the sun's face, hurling clouds of matter toward the Earth and lighting auroras far from their usual haunts. The record-breaking flare itself came late in the run, past the Earth rather than into it. The most powerful flash ever measured was, for the planet, mostly a glancing miss, which is the clearest possible proof that the size of the flash and the severity of the blow are two separate questions. It was, fittingly, a flare that overflowed the very scale designed to contain it, a reminder that the sun's upper limit is set by the sun and not by our willingness to measure it. For all its precision and speed, though, the X-ray class carries a quiet and important limitation, and it returns us to the thread that runs through everything. The number grades, the flash, the light, and only the light. It is an exact measure of how brightly the sun flared in X-rays, and it arrives within minutes, faster than any other piece of information. But it does not tell you the thing you most need to know. It does not tell you whether that same eruption hurled a cloud of matter off the sun, nor how fast that cloud is moving, nor whether it is aimed at the Earth or out into empty space. The correlation is loose in both directions. Some of the largest X-class flares fire off no significant cloud at all and pass as little more than a radio blackout. Some of the most damaging clouds of matter are launched by flares of unremarkable class. The flash and the cloud are made together, but their sizes are not locked to one another, and the bright, fast, precisely measured flash is silent on the question that matters most. So the first number, for all that it tells the watchers in those opening minutes, is only the opening line. It confirms that the field is broken, it sizes the light, it triggers the radio blackout warnings, and then it falls quiet on the subject of the slower, heavier, far more dangerous half of the event. To learn whether the second messenger is coming, the watchers cannot keep staring at the X-ray trace. They have to turn to an entirely different kind of instrument, one that blots out the blinding disk of the sun and watches the darkness just beside it, hunting for the faint, expanding ghost of a billion tons of plasma pulling away into space. The instrument that finds the cloud works by imitating an eclipse. Left to itself, the sun is far too bright to let anything be seen close beside it. Its glare floods the field of view and drowns out the faint corona where an eruption first appears. So the coronagraph carries its own small disk, an occulting mask held precisely in front of the sun's image, blotting out the blinding surface and leaving only the darkness around the rim. The trick was perfected in the 1930s by the French astronomer Bernard Liot, who grew tired of waiting for the rare minutes of a natural eclipse and built an instrument that could manufacture one on demand, on any clear day, for as long as he wished to watch. Every coronagraph since, on the ground and in space, is a descendant of his patience. With the disk itself hidden, the tenuous outer atmosphere springs into view, and against that darkness a launched cloud of plasma can be caught as it climbs away from the sun and expands into space. For most of a working lifetime now, one such instrument aboard a spacecraft called SOHO, parked far out on the sunward side of the Earth, has kept this artificial eclipse running without pause, photographing the space around the sun over and over, so that when a cloud erupts it is caught in frame after frame, swelling outward, and its progress can be tracked. What the coronagraph reveals is the second messenger, the one Carrington never knew was coming, the coronal mass ejection. Where the flare is a burst of light, the coronal mass ejection is a burst of substance. It is a colossal cloud of plasma, often billions of tons of it, threaded through with a coil of the sun's magnetic field and flung bodily off the star, sometimes in close company with a flare, sometimes more or less on its own. If the flare is the lightning, sudden, blinding, and gone in an instant, then the coronal mass ejection is the storm front behind the lightning, slow and massive and freighted with consequence, the part of the weather that actually arrives and does the damage. The two come from the same upheaval, but they are utterly different things, traveling on utterly different terms. The most important of those terms is speed, because speed is where the warning lives. The flash, made of light, allows no warning at all. The cloud, made of matter, is far slower, and in that slowness lies the entire margin we have to work with. A typical coronal mass ejection takes something between 1 and 3 days to cross the distance from the sun to the Earth. The slow ones can dawdle for the better part of a week. The very fastest, the rare monsters that clear the path ahead of them, can make the crossing in under a day, as the Carrington cloud did in its 17 hours. The forecaster watching the coronagraph measures the cloud's apparent speed by comparing one image with the next, sees how far it has traveled between frames, and from that estimates when it will reach the Earth. Days, or hours, of notice can be wrung from those few photographs. The whole apparatus of space weather prediction comes down, in the end, to this. The matter is slow enough to be seen leaving and timed on its way, and the light that announced it has already given the forecaster a head start in knowing where to look. There is a particular sight on the coronagraph that quickens a forecaster's pulse. When a cloud erupts off the side of the sun, heading away across space, it appears as a bright bubble climbing off one edge of the masked disk. But when a cloud is launched straight toward the Earth, or straight away from it, the geometry changes what we see. The cloud appears to balloon outward in every direction at once, swelling as a faint ring all the way around the hidden sun, because it is expanding toward the camera and we are looking down its throat. This is called a halo, and a halo on the coronagraph is the signature that a cloud is heading along the line between the sun and the Earth. It is the difference between a storm that will sail past and a storm that may be aimed at us. Read off a single ghostly image. There is a catch even here, for a cloud erupting on the far side of the sun and racing away from us throws up a halo just as round as one bearing down on us. To tell an oncoming storm from a departing one, the forecaster checks where on the sun the eruption began. A halo born from an active region on the visible, Earth-facing disk is the one to fear. And here the story arrives at its cruelest subtlety, the point where a warning measured in days collapses into a warning measured in minutes. Knowing that a cloud is coming, and roughly when, is not the same as knowing whether it will do any harm, and the thing that decides the harm cannot be seen from the coronagraph at all. The Earth is wrapped in its own magnetic field, the magnetosphere, which ordinarily behaves like a shield, turning aside the steady wind of particles from the sun. A coronal mass ejection carries its own magnetic field, coiled up inside it, and whether that cloud delivers a glancing nudge or a body blow depends almost entirely on which way its field happens to point when it arrives. If the cloud's field points the same way as the Earth's where they meet, the shield holds, the cloud is largely deflected, and even a fast, massive, perfectly aimed ejection may pass with little more than a flicker. But if the cloud's field points the opposite way, southward, against the Earth's own, then the two fields reconnect at the boundary, exactly the process that powered the flare in the first place, and the shield springs open like an unlatched gate. Energy and particles pour through the opening, and the full storm breaks loose. The agonizing part is that we cannot tell, from days away, which way the cloud's hidden field is pointing. The coronagraph shows the cloud's size, its speed, its direction, but not the orientation of the magnetic coil buried inside it. That single decisive fact stays hidden through the entire crossing, through all those carefully counted hours of warning, and is revealed only when the cloud sweeps past a spacecraft stationed well ahead of the Earth, a vantage point that buys, at the cloud's speed, somewhere between a quarter of an hour and an hour of final notice. For days, the forecasters can say that a storm is coming, and when. Only in that last short interval, as the cloud brushes the forward sentinel, do they learn whether it will be severe or slight. The warning is long, and the part of it that matters most is desperately short. When the field does point south and the gate swings open, the cloud's arrival is abrupt. It slams into the front of the magnetosphere at a speed measured in hundreds or thousands of kilometers a second, compressing the shield, driving it inward, and setting the whole vast structure of the Earth's field ringing like a struck bell. Instruments on the ground register the jolt in the same instant, a sudden sharp step in the magnetic record that marks the moment of impact. The shield does not break, but it is shaken to its foundations, and a geomagnetic storm begins, a disturbance that can last for hours or days as the cloud sweeps over and past the planet, pouring its energy into the magnetosphere and lighting it up from within. This is the second half of the blow, the half that Carrington felt as the telegraph caught fire 17 hours after his quiet morning at the eyepiece. We have come a long way since then in our ability to see it coming. We can watch the cloud leave the sun, measure its speed, judge its aim, and count down the hours to its arrival, where Carrington could only wait in ignorance through a calm that was no calm at all. And yet, for all that hard-won foresight, the very last and most important fact about the storm still hides until the cloud is almost upon us, locked inside the physics of the thing, in a way no improvement in instruments can fully undo. The warning has grown longer and sharper across a century and a half, and a stubborn core of it remains, by nature, until the end. No sharper lens, and no faster computer, can photograph the inside of the cloud from afar. The decisive fact simply does not announce itself until the matter is nearly upon us. When the gate does open, and the storm does break, the energy that floods in has to go somewhere. Much of it spirals down toward the poles to light the sky, and some of it works its way into the rock of the Earth and the long metal lines we have laid across its surface, the wires and cables and pipelines and rails that lace every modern country together. It is there, in the conducting ground and the grid strung over it, that a storm in the sky finishes its journey and becomes something that can reach into a city and switch off the lights. The path from a storm in the sky to a current in the ground runs through one of the oldest laws of electricity. Nearly 2 centuries ago, Michael Faraday discovered that a changing magnetic field will drive an electric current in any conductor it passes through. This single principle is what turns a generator and what charges a phone, and it is also what arms a geomagnetic storm. During a great storm, the Earth's magnetic field does not merely tilt or strengthen. It convulses, shuddering and swinging, as enormous rivers of electric current surge through the upper atmosphere over the poles. This overhead torrent, the auroral electrojet, can carry more than 1,000,000 amperes, swelling and lurching as the storm builds, a vast and unsteady current strung across the sky 100 kilometers up. A magnetic field that is changing that violently, draped over a planet laced with conductors, cannot help but induce currents in them. The rock of the Earth carries some, but far more flows into the long metal lines we have strung across the surface, the very things built to carry current, which now find themselves carrying a current no one switched on. These are the geomagnetically induced currents, and what makes them dangerous to a power grid is that they are the wrong kind of current in the wrong place. The grid is built for alternating current, electricity that reverses direction many times a second in a smooth, predictable rhythm. The current a storm induces is almost the opposite, a slow, wandering, nearly steady flow, closer to the direct current of a battery, drifting through the network on timescales of minutes. It enters through the points where the great high-voltage transformers are earthed, and once inside such a transformer, it does something its designers never intended. It biases the core, pushing the iron into saturation so that the transformer can no longer do its job cleanly. It begins to overheat. It draws enormous gulps of reactive power from the system, throwing the careful balance of the grid into disarray, spilling distortion down the lines, and tripping the protective relays meant to guard against faults. In the worst case, the protections cascade, one trip triggering the next, and a network that took decades to build can throw itself into darkness in seconds. Worse still, the heating can ruin the largest transformers outright, and those are not items kept on a shelf. Each is the size of a house, built to order, and replacing one can take many months. Replacing many at once could take far longer than that. All of this stopped being theoretical in the small hours of the 13th of March, 1989. A large and active region of the sun had thrown a powerful cloud of plasma toward the Earth, and when it arrived, it set off one of the most severe geomagnetic storms of the modern era. The province of Quebec lay almost perfectly positioned to suffer for it. Its power utility drew electricity from immense hydroelectric stations far to the north and carried it southward over very long transmission lines that ran across the ancient rock of the Canadian Shield, some of the oldest and most electrically resistant stone on the planet. That resistant bedrock is the crucial detail. Because the ground itself conducted so poorly, the induced currents took the easier path, flooding into the grid instead. High latitude put the province almost beneath the storm's worst fury. The long lines gathered the induced voltage along their length, and the stubborn rock funneled the current into the wires. Everything that could make a grid vulnerable was present at once. The collapse, when it came, was almost instantaneous. The induced currents struck the transformers and the protective systems began to trip, and once the first protections fell, the rest followed in a cascade that swept through the network faster than any human hand could intervene. In about 90 seconds, the entire Quebec grid went down. 6 million people lost power in the depth of a Canadian winter night, and the lights, the heat, and the machinery of an entire province stayed dark for around 9 hours, while engineers fought to bring the system back. In Montreal, the underground railway halted. The airport went dark. Traffic signals died across the city, and people woke in cooling homes to a winter morning, with no obvious reason for why everything had stopped. Offices and schools stayed shut. For most of those 6 million, the cause was not a storm they could see, but a clear, cold, perfectly ordinary-looking dawn. There had been no dramatic warning on the ground, no thunder, no visible cause. One moment, the grid was carrying its ordinary load, and 90 seconds later it was gone, brought down by a cloud of solar plasma that had left the sun 3 days earlier. The same storm did not stop at Quebec. Far to the south, at a nuclear plant in New Jersey, a great transformer was so badly overheated by the induced currents that it was damaged beyond repair and had to be replaced. Across much of the planet, the sky lit up. Auroras normally confined to the far north were seen over Florida, over Cuba, over the lower United States. The same beauty that had blazed over the Caribbean in Carrington's storm, draped now over a world that had built far more for the storm to break. A single eruption on the sun had reached across one hemisphere and touched a power grid, a nuclear station, and the night skies of the tropics, all from the one upheaval of a distant magnetic field. What happened to Quebec can, in principle, happen to any grid that shares its weaknesses, and those weaknesses are not unusual. The danger rises with geomagnetic latitude, so the grids of Canada, the northern United States, the United Kingdom, and Scandinavia sit closer to the firing line. It rises with the length of the transmission lines, which gather more induced voltage the farther they run. And it rises wherever the underlying rock is a poor conductor, or along coastlines where land meets sea, and the sharp contrast in conductivity concentrates the currents. Much of the modern, industrialized, heavily wired world carries one or more of these traits, which is precisely why a single winter night in Quebec became a permanent lesson for everyone who keeps the lights on. And Quebec, sobering as it was caused by a storm well short of the worst the sun can do. The 1859 event was substantially stronger, and the sun is capable of stronger still. This is why the Carrington event is studied not as history but as a forecast. When researchers ask what a storm of that magnitude would do to the grid we have now, far larger, far more interconnected, and far more essential than the grid of 1989, the more serious estimates are genuinely alarming. Formal assessments, including a much-cited national scientific review and studies commissioned by the insurance industry, have tried to put bounds on the damage, and what they describe is not reassuring. A Carrington-class storm striking a modern, continent-spanning network could, in the gravest scenarios, push many of the largest transformers into failure at once, across whole nations, and because those transformers are built to order and shared between few suppliers, the resulting damage might take not hours, but months or years to undo. The cascade would not stop at electricity. The pumps that move water and fuel, the systems that handle payments, the networks that carry communication, all of it ultimately rests on the grid, and a long, wide loss of power would reach into every one of them. The numbers attached to such scenarios run into the trillions, and the recovery times into years. Though it must be said plainly that these are projections, not certainties, built on a storm that struck before any of the threatened infrastructure existed. The honest position is that we do not know exactly how bad it would be, only that the worst plausible case is bad enough to take very seriously. This is the point at which the warning earns its keep. A grid is not helpless against a storm it can see coming. Given enough notice, operators can lighten the load on the network, hold extra capacity in reserve, reconfigure the system to spread the strain, and in some cases take the most vulnerable transformers out of the firing line before the current arrives. None of that is possible if the storm lands unannounced, and all of it depends on the hours bought by watching the cloud cross the gap. The long, imperfect warning, the days of notice from the coronagraph, and the final confirmation from the forward sentinel is in the end a warning meant for the woman at the control desk of a power company who can ride out a managed storm but cannot recover from a surprise. The whole point of seeing the blow coming is to be standing differently when it lands. Not all of the storm's energy, though, ends in the ground and the grid. A great share of it is steered down along the Earth's own magnetic field toward the poles, where it pours into the thin upper air and sets it glowing. The same disturbance that can darken a province paints the most extraordinary light show our planet has to offer. And to understand the storm fully, we have to follow that energy up to where the sky itself catches fire. Follow the energy upward, and it leads to the poles, because the poles are where the Earth's magnetic field gathers itself in. The field that wraps the planet is not a uniform thing. Its lines sweep out into space above the equator and plunge back down at the north and the south, converging on the magnetic poles like the seams of an orange drawing together at each end. Charged particles caught in that field cannot cross its lines, only slide along them, and so the electrons set loose and energized by the storm are channeled down those converging seams, funneled out of the vast volume of the magnetosphere and into two tightening rings around the top and bottom of the world. These descending sheets of current, pouring down the field into the poles, are the conduit along which a storm in space delivers itself to the sky. They were imagined decades before any instrument could confirm them, and mapping them would one day help prove where the auroral light truly comes from. What threatens the grid, as a current in the ground, arrives in the sky as a rain of particles, guided to the poles by the planet's own field. When that rain reaches the thin upper air, somewhere around 100 kilometers up and higher, it begins to collide with the atoms and molecules of the atmosphere, and each collision passes energy to the gas. An atom struck this way has one of its electrons knocked into a higher, agitated state, and an electron in such a state does not stay there. It falls back, and as it falls, it releases the borrowed energy as a flash of light of a very particular color. Multiply that single flash by uncountable trillions, spread across the sky, and you have an aurora, the upper atmosphere itself made to glow, a sheet of excited air lit from within like the largest neon sign imaginable, draped in curtains and arcs across the polar night. The colors are not random, each is a fingerprint. The commonest, the soft green that defines the aurora in most people's minds, comes from atomic oxygen at altitudes of roughly 100 to 300 kilometers, glowing in the particular green it favors when struck. Higher up, above 300 kilometers, where the air is thinner still, oxygen gives off a deep red instead, the rare crimson that crowned the greatest historical storms and frightened those who saw it. Lower down, at the ragged bottom edges of the curtains, nitrogen contributes its own blues, purples, and pinks. Read the colors and you are reading the chemistry and the altitude of the glow directly. The green tells you oxygen at middle height, the red tells you oxygen far higher, the violet fringe tells you nitrogen near the base. The sky is, in effect, labeling itself. The light an excited gas gives off is as distinctive as a signature, the same principle that revealed the impossible heat of the corona, and the aurora is simply our own air, signing its name across the night in the colors of the gases it is made from. These curtains do not form a cap sitting neatly over the pole. They trace a ring, the auroral oval, drawn around the magnetic pole at some distance from it, marking where the storm's field lines come down. In quiet times, the oval is a thin, high-latitude band, and you must travel far north or far south to stand beneath it. But as a storm strengthens, and the magnetosphere fills with energy, the oval swells and slides toward the equator, reaching down over latitudes that ordinarily never see it. This is why the spread of the aurora is itself a measure of the storm, a faint ring over the Arctic on a calm night, It bulges down to the northern United States in a strong storm, and in the greatest storms of all, the Carrington event and the storm that took Quebec, it pushes so far that people in the tropics look up and see the sky on fire. The aurora is a gauge you can read with the naked eye. The farther from the pole it is seen, the harder the sun has struck. It works backward in time as well. Records of auroras seen at improbably low latitudes, set down by startled chroniclers in ancient China, around the Mediterranean, and across medieval Europe, now serve as evidence of great solar storms that struck long before any instrument existed to measure them, the sky's own written archive of the sun's worst days. It happens at both ends of the world at once. The northern lights and the southern, the aurora borealis and the aurora australis, are near mirror images of each other, lit in the same moment by the same particles sliding down the two ends of the same field lines. A great display over northern Canada has a twin blazing over the southern ocean that almost no one is there to see. The whole planet, north and south together, lights up along the seams of its magnetism whenever the sun reaches it hard enough. For almost all of human history, these lights were red, but read as portents rather than physics. Peoples across the far north and far south wove them into story. The spirits of the dead, the armies of the sky, dragons and battles, and the displeasure of gods, signs to be feared or revered. They were a message in the sky that everyone could see and no one could decode. The same predicament met at the very beginning, the message arriving and no one able to read it. The decoding, when it came, was the work of a Norwegian named Christian Birkeland, who at the start of the 20th century proposed that the lights were caused by charged particles streaming from the sun and steered to the poles by the Earth's magnetic field. To make the case, he built a small magnetized sphere, a terrella, suspended it in a vacuum chamber, and fired a beam of electrons at it, and watched glowing rings settle around the little globe's poles, a working aurora built on a laboratory bench. He had very nearly the whole picture, decades before instruments could confirm it, and like Carrington before him, he was doubted in his lifetime and vindicated long after. His face would eventually look out from his country's banknotes, a quiet monument to reading the invisible correctly. He died far from home and never saw himself fully proven right, which is the recurring fate of those who learn to read the sun a generation too early. Today the lights have become a number. The same disturbance that paints them is measured continuously by magnetometers around the world and distilled into a global index of geomagnetic activity, a scale running from 0 for a perfectly quiet field up to 9 for the most violent storms. Forecasters use it to say in advance how disturbed the field will be and how far toward the equator the aurora is likely to reach, so that the curtains an ancient watcher would have taken for an omen are now an entry on a forecast, posted for aurora chasers and grid operators alike. The same glow means opposite things to the two of them. To the traveler pulling off a dark northern road to watch, it is the spectacle of a lifetime. To the engineer at the control desk, it is the visible warning that currents are running in the ground. The omen has become a diagnostic, and the dragon in the sky has become a datum on a screen, but it is, underneath, exactly the same light. The reading is not even finished. Only a few years ago, aurora chasers in the far north kept photographing a narrow mauve ribbon that crossed the sky in a way no ordinary aurora should, and when they brought it to the attention of scientists, it proved to be a genuinely new phenomenon, a river of hot gas streaming through the upper atmosphere, since given the unassuming name Steve. It was found not by a satellite or a great observatory, but by amateurs with cameras and patience, the same combination of careful, stubborn looking that began this entire story, still turning up things the professionals had missed. That light is the storm at its gentlest, spending its energy harmlessly on the thin air, and asking nothing of us but that we look up. The same particles, the same charged and disturbed environment, are nothing like so kind to the things we have lifted above the atmosphere, into the orbits where there is no air to glow, and no protection, but a thin metal skin. To follow the storm into that realm is to leave the beauty behind and meet the hazard at close range, in the fragile, crowded, and increasingly crucial band of space where our satellites fly. A satellite has none of the protections we take for granted on the ground. It flies above the air that absorbs the flash, above the magnetic shelter that thickens nearer the surface, exposed in the open to whatever the sun sends. The same particles that spend themselves harmlessly on the upper atmosphere, lighting the aurora and then fading, strike a spacecraft as a direct and unsoftened assault. There is nothing between the machine and the storm but its own thin skin, and the storm has several different ways of getting through it. The first is the quiet menace of charge. A geomagnetic storm fills the space around the Earth with fast electrons, energizing the great radiation belts that ring the planet until they breed swarms of so-called killer electrons, relativistic and penetrating, that can linger for days after the storm itself has passed. As a satellite flies through that thickened sea of charged particles, they settle onto its surfaces and, worse, bury themselves inside its insulating materials, where they cannot easily drain away. Charge builds up in pockets across and within the spacecraft, and different parts of it come to sit at wildly different voltages, exactly the condition that precedes a spark. When the difference grows too great, the charge equalizes the only way it can, in a sudden internal discharge, a tiny bolt of lightning loosed inside the machine. That discharge can punch through circuitry, corrupt a command, burn out a delicate component, or send the whole satellite tumbling into confusion. A great many of the anomalies that afflict spacecraft, and some of the outright failures, trace back to this slow accumulation of charge and its abrupt, destructive release. The satellite is not struck from outside so much as turned against itself from within. The record is full of casualties. In the first weeks of 1994, 2 Canadian communications satellites lost control within hours of each other during a spell of intense electron activity, knocking out telephone, television, and data links across much of the country. One of them was recovered only after months of improvised effort. During the Halloween storms of 2003, a Japanese Earth observation satellite was crippled outright and never recovered. These are not freak events, but the routine arithmetic of flying delicate machines through a sea of charge that the sun can deepen without notice. The storm has a sharper weapon too. Among the particles in a severe event are some moving at a sizable fraction of the speed of light, energetic enough to drive straight through a spacecraft's walls and into the heart of its electronics. When one of these passes through a microchip, it can flip a single bit from one state to the other, and that flipped bit may mean a corrupted number, a scrambled instruction, or a sudden unwanted reset. Engineers design around this with redundancy and error correction, with systems that vote against one another and catch the lie, but the hazard never fully goes away, and in the thick of a storm, the rain of such particles intensifies, and with it the rate at which the machines must catch and correct their own mistakes. Then there is the subtlest effect of all, the one that reaches down and tugs at the orbits themselves. When a flare's flood of ultraviolet and a storm's pouring energy reach the upper atmosphere, they heat it, and a heated gas expands. The outermost layers of the atmosphere, the tenuous fringe through which low-flying satellites move, swell, and rise, so that a spacecraft which was orbiting through near vacuum suddenly finds itself plowing through measurably thicker air. Thicker air means more drag, and more drag means the satellite is slowed, its orbit lowered, its careful altitude eaten away faster than planned. For a single craft, this shortens its working life. For the whole population of objects in low orbit, the tens of thousands of satellites and spent stages and fragments that must be tracked to keep them from colliding, a storm that puffs up the atmosphere shifts all of them at once. Unpredictably, and for a time the careful catalog of who is where becomes a great deal less certain. That uncertainty matters more every year, as the orbital lanes grow more crowded, and the work of keeping satellites from colliding depends on knowing each object's position to within a small margin. A storm that nudges the entire catalog at once forces controllers to re-find thousands of objects, and for a while, raises the odds of a collision that no one saw coming. This is not a hypothetical. Early in 2022, a company launched a batch of several dozen small communications satellites into a low initial orbit, intending to raise them gradually to their working altitude. A geomagnetic storm, modest as such things go, arrived almost immediately afterward and heated the upper atmosphere just enough to thicken the air the new satellites were climbing through. The added drag was more than they could overcome from so low a start. Most of the batch never reached a safe altitude. They were dragged back down and burned up in the atmosphere within days of launch. A fleet lost not to an explosion or a collision, but to a stretch of slightly heavier air, warmed by a storm that would barely have registered on the ground. It was a sharp, modern lesson in how a disturbance, far too small to darken a city, can still reach up and pull spacecraft out of the sky. Against all of this, the operators of a satellite are not without recourse, and their best defense is to see the storm coming and prepare the machine to meet it. A spacecraft warned of a severe event can be placed into what is called a safe mode, and it is worth being precise about what that means, because it is not a rest and not a surrender. It is a deliberate defensive configuration. The most sensitive systems are powered down, precision operations are suspended, instruments that could be damaged are turned away or switched off, and the craft is reduced to a hardened, minimal state designed to survive a hostile few hours intact. A ship does the same thing when it battens down before a gale, not sleeping but bracing, trading its ordinary work for the single task of coming through undamaged. When the storm passes, the systems are brought back up in order, the instruments reopened, and the satellite returned to its duties. Whole fleets can be commanded into this posture together when a severe storm is forecast, and launches can be held on the pad until the sun has quietened. The safe mode is the orbital expression of exactly the principle that governs all of it. A warning is only worth having if you can do something with it, and a satellite that knows the storm is coming can be standing in a very different posture when it arrives. What gives all of this its weight is how much we have now placed in harm's way. The orbital band that a storm can reach is more crowded than at any moment in history, and growing more so by the month, filled with constellations numbering in the thousands, and the services riding on those machines have woven themselves into the foundations of ordinary life. The signals that guide ships and aircraft and tractors, the precise timing that stamps financial transactions and synchronizes communication networks, the eyes that watch the weather and the crops and the coastlines, all of it lives in orbit now, exposed to the same charging and drag and particle rain that a great storm brings. Every satellite added to the sky is another stake placed on the table, another asset that a sufficiently violent sun could reach, and much of that dependence stays invisible until it fails. The same satellite timing that lets a telephone call connect also stamps the world's financial trades and keeps the pulses of separate power grids in step. Degraded across a hemisphere for a day, and the disruption surfaces in places that seem to have nothing to do with space at all. The hazard has not grown. The sun is no fiercer than it was in Carrington's day. What has grown, steeply and recently, is the amount we have lifted into the line of fire. And yet, dangerous as the charging and the drag and the bit flips are to machines, they are survivable. Designed around, ridden out. The deepest danger the sun poses falls not on satellites but on living bodies, and it comes in the form the storm reserves for its most violent moods. A flood of particles accelerated almost to the speed of light, the hardest and most penetrating thing the sun can throw across space. On the ground, beneath the air and the magnetic shield, we are spared it. Out where the astronauts go, and on any journey beyond the Earth's protecting field, it becomes the single gravest threat the sun presents to human. To reckon with it, we have to follow those particles outward, past the shield, to the places where a human body would have to meet them with nothing in between. The particles that threaten a human body are not the gentle drizzle that lights the aurora. They are the hardest thing the sun produces, protons and the bare nuclei of heavier atoms, flung out of a flare and whipped to tremendous energies, some of them moving at a large fraction of the speed of light. They are accelerated partly in the reconnection itself, and partly in the shock front that a fast cloud of plasma drives ahead of it as it plows through space. A shock that acts like an enormous natural particle accelerator, picking up protons and hurling them outward far faster than the cloud that made it. When a great eruption occurs, this radiation pours off the sun in a flood, and the flood is what we mean by a solar radiation storm. These particles occupy a strange middle ground in the timing of the warning, and it is worth placing them carefully. The light of the flare arrives in 8.5 minutes and gives no warning at all. The heavy cloud of plasma takes its day or more, and gives the longest warning of any of the sun's messengers. The fast particles fall in between, moving at nearly the speed of the light that announced them. The quickest of them reach the Earth within tens of minutes of the flash, sometimes less. So a radiation storm begins almost on the heels of its own announcement. The flash arrives, the forecaster reads it, and within a quarter of an hour to an hour, the first protons are already sleeting through near-Earth space. It is a short warning, far shorter than the one the cloud allows, but it is not quite nothing, and out where it matters most, those few minutes are the difference between safety and grave danger. The reason these particles matter so much to flesh, where they barely trouble a well-built machine, is that they are ionizing radiation of the most penetrating kind. A fast proton driving through living tissue tears electrons from the molecules in its path, and among those molecules is the DNA that every cell depends on. A modest dose raises the long-term risk of cancer by leaving damage that the body's repair machinery may not perfectly mend. A very large dose, of the kind a severe storm could deliver to an unprotected person, causes acute radiation sickness, the swift and dangerous breakdown of the body's fastest dividing tissues. On the surface of the Earth, we are shielded twice over and never think about it. The magnetosphere turns aside a great deal of the incoming flux, and the deep blanket of the atmosphere absorbs almost all of what gets through. We live at the bottom of a protective ocean of air, and the radiation storms break harmlessly far above our heads. The protection is not quite total, even so. The very strongest events accelerate particles to energies high enough that, when they strike the upper atmosphere, they set off cascades of secondary particles that reach all the way to the ground, registered by detectors built to count them. People in an airliner at cruising height, especially on the polar routes where the magnetic shield is weakest, sit above much of the protective air and take a small but real extra dose during such a storm, which is one reason airlines will sometimes move flights to lower latitudes and lower altitudes when the sun is firing hard. Even at the bottom of our ocean of air, the largest storms are faintly felt. Astronauts do not have that luxury. Aboard a station orbiting a few hundred kilometers up, a crew still sits within the magnetosphere and keeps much of its protection, but they are higher than the sheltering bulk of the atmosphere and markedly more exposed than anyone on the ground, especially when their orbit carries them over the high latitudes or through the weak spot in the Earth's field where the inner radiation belt dips low. When a strong proton event is detected, the crews of orbiting stations have a standing response. They move into the most heavily shielded part of the structure, a region surrounded by water tanks, equipment, and stored supplies, and wait there, behind as much mass as the station can put between them and the sun, until the worst of the storm has passed. Even in ordinary conditions, a crew in orbit absorbs far more radiation than anyone on the ground, and the total a person may accumulate over a career is one of the firm limits on how long they can be allowed to fly. It is once again the same principle in another form, a warning acted upon, a body placed deliberately behind a shield because something is known to be coming. Beyond the magnetosphere, the danger changes from serious to potentially lethal, because out there, the planet's shield is simply gone. The Moon has no global magnetic field and no atmosphere worth the name. Mars has only the thinnest skin of air and no protective field of its own. An astronaut crossing the gulf between worlds, or standing on the surface of the Moon, would meet a great solar radiation storm with nothing between their body and the sun but the walls of their craft or their suit. How real this threat is was written, by the narrowest of margins, into the history of the Apollo program. In August of 1972, between the flight of Apollo 16 in the spring and Apollo 17 at the year's end, the sun unleashed one of the fiercest radiation storms of the era. It was not a single flash but the better part of a week of violent activity, and the flood of protons it produced was savage. No one was on the Moon to receive it. But had the timing fallen differently, had a crew been in transit or walking the lunar surface when that storm broke, the dose they would have absorbed could have caused serious illness, and in the worst reckoning, might have been enough to kill. The astronauts who walked on the Moon were, in this one respect, fortunate in their calendar. A future crew bound for Mars, exposed for months at a stretch, will not be able to rely on luck. Protecting them comes down to a question of mass, and, surprisingly, of the right kind of mass. To stop these particles, you need material between them and the body, but not just any material. The obvious choice of dense metal turns out to be a poor one. When a fast, heavy nucleus strikes a heavy atom like lead, it can shatter it and spray out a shower of damaging secondary particles, so that a thick metal wall sometimes makes the radiation behind it worse rather than better. The materials that shield best, per kilogram carried, are rich in hydrogen, the lightest element, which absorbs the impact without breeding those destructive showers. Water is excellent, so is ordinary plastic. So, conveniently, are the food, the water, and even the waste that a crew carries with them, which is why a deep space storm shelter can be built, in part, out of the supplies the mission needs anyway, packed around a small protected core. On the Moon or Mars, the shield is already underfoot, a habitat buried beneath a few meters of the local soil, the loose broken rock called regolith, or tucked inside a natural lava tube, would let the crew ride out a storm under the same kind of protection the Earth's atmosphere gives us for free. More exotic ideas circulate, including wrapping a ship in a magnetic field of its own to mimic the planet's shield. But for now, the practical answer remains stubbornly simple. Put enough of the right matter between the crew and the sun, and wait. For a crew far from home then, the whole abstract architecture of the warning collapses into a single, vivid, human act. There is no air above them to absorb the blow, and no field around them to turn it aside. There is only the light, racing ahead of the protons, and the few minutes it buys. A monitor catches the flash. An alarm sounds. And somewhere out beyond the Earth, men and women stop what they are doing, and move, quickly, toward a small room walled with water and supplies, sealing themselves behind as much mass as they can reach before the hardest of the particles arrive. All of it, the reconnection, the spectrum of light, the classification, the slow cloud, and the fast protons, comes down out there to people running for shelter on the strength of a warning written in light. It is the most literal possible answer to the question the sun keeps asking. Can you read the message in time to act on it? That they can act at all, in orbit or on a distant surface, or at the control desk of a power company, depends on something watching the sun every second and turning what it sees into a warning fast enough to use. The flash that sends a crew running for shelter, the cloud speed that lets a grid prepare, the safe mode order that hardens a satellite, none of it exists without a network of eyes trained on the sun, without pause, and a community of forecasters who never close their doors. That watching apparatus, built up over a single human lifetime from almost nothing, is what turns the sun's warning from a thing that merely happens into a thing we can use. Consider how far that watch has come in the span of a single life. Carrington had a telescope, a screen, and a pencil, and when the flash came, he could only sketch it and wonder. The people who watch the sun today command a fleet of instruments scattered across the inner solar system, trained on the star without pause, returning images and measurements by the second, and between them they have turned the reading of the sun from a matter of luck into a standing institution. That institution was not built all at once, nor entirely by foresight. Much of it grew in response to hard lessons, the storms that took down grids and crippled satellites teaching, each time, that the watch needed to be sharper and the warnings faster. It is worth meeting the principal eyes of that fleet, because each was built to catch a different part of the warning. The eldest of them keeps station far out on the line between the Earth and the Sun, at a point 1.5 million kilometers away, where the pull of the two bodies balances in such a way that a spacecraft can hang there indefinitely, always facing the Sun, never eclipsed by the Earth. Such balance points, where the gravity of the Earth and the Sun conspire to hold a small object more or less still relative to both, are among the most prized addresses in the solar system, precisely because an instrument left there needs almost no fuel to keep its uninterrupted view. The observatory parked at that point has watched the sun for the better part of 3 decades, far longer than anyone planned, and it carries the artificial eclipse coronagraph met earlier, the instrument that blots out the disk to catch the clouds pulling away. From its steady vantage, it has logged storm after storm, and almost incidentally, by spotting them as they dive toward the sun, it has discovered thousands of comets along the way. It is the patient grandfather of the fleet. Nearer to home, a younger observatory stares at the sun's face in extraordinary detail, photographing the whole disk every few seconds in a range of ultraviolet colors chosen to pick out gas at different temperatures. This is the instrument behind most of the imagery the world now recognizes as the sun. The seething surface, the arched loops standing over the active regions, the ribbons blazing as a flare erupts, all of it caught in a continuous, high-speed stream that lets forecasters watch an active region twist and brighten and finally break almost in real time. Each wavelength it records is tuned to gas at a particular temperature, so that flicking between them is like peeling the sun apart layer by layer, from the cool surface to the million-degree corona, and the flood of images it returns each day is large enough to keep whole archives of researchers busy for years. Where the older sentinel watches the space around the sun, this one watches the sun itself, and watches it closely enough to see trouble building. Some of the most valuable watching, though, is done from the side and from behind. A pair of spacecraft was sent out into the Earth's own orbit, one running ahead of the planet and one trailing behind, so that between them and the instruments near Earth, the sun could be seen from several angles at once, and a cloud could be caught in profile as it left, its true speed and breadth measured far more reliably than from head-on. They also opened a view of the sun's far side, the hemisphere turned away from us, which matters more than it might seem, because the sun turns, and an active region already wound tight and primed to erupt can rotate around the limb and into the line toward Earth with little notice. Seeing it coming, before it comes around, can turn a surprise into a forecast. There is even a way to glimpse the far side without flying behind the sun at all. The sun rings faintly with sound waves coursing through its interior, and by reading how those waves are disturbed, the way a struck bell sounds different with a hand pressed to its far surface, the hidden hemisphere can be roughly mapped from the near side alone, a great active region on the far side announcing itself through the sound it casts ahead. It is an extraordinary thing to map a face of the sun that no telescope can see by listening to the star, rather than looking at it. Then there is the small cluster of spacecraft that share the distant balance point with the old coronagraph and do the one job the imagers cannot. They wait directly in the path of the oncoming cloud and measure it as it arrives. These are the forward sentinels promised earlier, the craft that finally read the orientation of the cloud's hidden magnetic field as it sweeps past them, and so resolve the agonizing question of whether the storm will reconnect with the Earth's shield or slide harmlessly by. They buy that last knowledge at a steep price in time. Stationed only a little ahead of the Earth, they hand over the decisive fact with perhaps a quarter of an hour to an hour to spare. It is the shortest and most important warning in the whole chain, the final word after days of waiting. The watch is kept from the ground as well, and the ground holds one advantage no spacecraft has yet matched: sheer size. On a Hawaiian summit stands the largest solar telescope ever built, its main mirror 4 meters across, and it can resolve features on the sun as small as about 30 kilometers. Fine enough to make out the individual threads of magnetic field that weave through the surface, structures no instrument had ever seen so sharply before it began its work. Building it meant solving a peculiar problem. A 4-meter mirror gathers so much sunlight that it concentrates enough heat to melt metal, and an elaborate system of cooling and shielding had to be devised simply to keep the telescope from destroying itself while staring at the very thing it was made to study. Where the space telescopes give breadth and constancy, watching the whole sun all the time, this great eye gives depth, picking apart the fine magnetic detail in which the seeds of a flare are sown. All of these eyes feed, in the end, into rooms full of people. The forecasting of space weather is done at national centers that never close, where forecasters watch the incoming streams around the clock, the way meteorologists watch the weather, and issue the alerts that send the warnings down the chain. They run models that take a cloud's measured speed and direction and compute, across a simulated map of the inner solar system, when and how hard it should strike. And they bring human judgment to the ambiguous cases, the halo that might be coming or going, the active region that looks dangerous but has not yet broken. The sun belongs to no country, and the watch over it is correspondingly shared. Centers on different continents trade their data and their forecasts freely, because a storm bound for the Earth is bound for all of it, and the warning is only as good as the weakest gap in the watch. A forecaster's day is a steady triage of the sun's moods, ranking the active regions by how dangerous they look, judging whether a fresh halo is inbound or departing, deciding when an alert is warranted and to whom it should go: to the airlines, the grid operators, the satellite controllers, the agencies that fly people. When the call is made, it travels in minutes to everyone who has arranged to receive it, and the data beneath it is shared across borders without charge, on the simple understanding that no one watches the sun alone. Step back from the individual instruments, and the achievement is genuinely striking. Within the lifetime of people still living, we have gone from Carrington's 17 hours of complete ignorance, a man who saw the flash and had no idea anything was coming, to a continuous, global, second-by-second vigil that can catch a flare as it ignites, time a cloud across the gulf, read its hidden field in the final hour, and turn all of it into warnings precise enough to harden a grid, safe a satellite, and send a distant crew to shelter. The warning that was once a buried accident in the records has been rebuilt, deliberately, into a working system. We have learned, in a century and a half, to read the sun. And yet there is one thing all of this watching still cannot do, one stubborn limit that no instrument in the fleet has overcome. We can see the active region wind tight. We cannot say when it will snap. We can catch the flash the instant it comes. We cannot predict it the hour before. We can time the cloud and read its field, but only after it has been launched and is already on its way. The deepest question, the moment of the break, and the true size of the next great storm, remains beyond us, and the closest the sun has come to teaching us that lesson in the satellite age was a blow most of the world never even knew it dodged. On the 23rd of July, 2012, The sun fired one of the most powerful storms of the space age, and almost no one noticed because it was not aimed at us. From an active region on a part of the sun turned away from the Earth, an enormous eruption tore loose. In truth, a pair of clouds launched in quick succession that merged into a single colossal front, racing outward at a speed approaching 3,000 kilometers a second. It crossed the distance that ordinarily takes a cloud 2 to 4 days, in roughly 17 hours, the same furious pace that had carried the Carrington storm across in 1859. By every measure that mattered, it was a Carrington-class event, perhaps larger, the worst the sun had produced in a very long time. And it was hurled into a part of space where the Earth simply was not. That it was measured at all was a stroke of fortune of a different kind. One of the two spacecraft sent ahead of and behind the Earth to watch the sun from the side was lying almost directly in the storm's path, and it flew straight through the heart of the cloud, recording its speed, its density, and the orientation of its magnetic field from the inside. And the orientation it recorded was close to the worst possible. The cloud's magnetic field pointed strongly southward, the very direction that throws open the Earth's shield. Had the storm been aimed at us, it would not merely have arrived. It would have found the gate already unlatched and poured straight through. For the first time in history, a monster of this scale was caught and measured in full, not reconstructed afterward from auroras and damaged telegraphs as Carrington's had been, but logged directly by an instrument standing in its path. We know exactly how severe it was because a machine took its measure as it passed. The unsettling part is how narrowly it missed. The sun turns roughly once a month as seen from the Earth, carrying its active regions around with it, and the region that fired this storm had rotated past the Earth-facing position only about a week earlier. Had the same eruption occurred a week or so sooner, the Earth would have been sitting squarely in front of it, and the full force of a Carrington-class storm, measured and undeniable, would have struck a planet wired and orbited and dependent as never before. We were not spared by any shield or any warning, or any act of preparation. We were spared by the calendar, by the accident of where the Earth happened to be standing in its orbit when the sun chose to let go. What it would have done, had it struck, is precisely the worst case sketched earlier, no longer as a projection from a 19th century storm, but as a measured reality that genuinely passed our way. The researchers who studied the cloud's recorded properties concluded that a direct hit could have rivaled or exceeded the Carrington event, with consequences for the grid, the satellites, and the timing networks at the very top of the range these hazards can reach, and that the world might have spent years repairing the damage afterward. The most important thing the near miss taught was not a number, though. It was that the worst case is not a relic of a less advanced age, not a thing that could only happen before we understood the sun. The sun still makes storms of that size. It made one within recent memory. We only failed to be hit by it. This raises the obvious and uncomfortable question of how often the Earth can expect to stand in the wrong place at the wrong moment. The honest answer is that the statistics are thin, because the instrumental record is short and the genuinely enormous events are rare. The estimates that have been attempted put the odds of a Carrington-class storm striking the Earth at something on the order of 1 chance in 10 across any given decade, which is neither a comfort nor a certainty, but it is emphatically not negligible. It is the sort of risk that, applied to anything else a society depends on, would be taken very seriously indeed. The blow is not a question of whether but of when, and the when is governed by a roll of the dice we do not control and cannot load. And here the story arrives at the hard wall that all the watching has not been able to breach. The reason a warning, however magnificent the system that delivers it, can never become a true prediction. The closest analogy is an earthquake. Geologists can map a fault, watch the strain accumulate along it across years, and say with confidence that a particular fault is dangerous and will, someday, rupture. What they cannot do is say when. The break depends on the precise breaking point of rock under stress, on details too fine and too hidden to measure, and so the strain can be tracked while the moment of release stays stubbornly unpredictable. A solar active region is the same kind of problem. We can watch it wind up, photograph its tangled field, measure its strain, and judge it dangerous. Forecasters can even assign it a probability, a 1 in 3 chance of a major flare in the coming day. But the actual trigger, the instant the current sheet thins past its limit and the field tears loose, depends on instabilities at scales too small and too sudden to see coming. The system seems to hover always on the edge of failure, poised so that the final push can come from a disturbance too slight to detect, which is why even the best forecasts deal in odds rather than moments. We can say a region is loaded. We cannot say when it will fire. The buildup is visible and the break is not, and that gap between them is the permanent residence of our ignorance. There is a second wall beside the first, and it concerns not when but how large. We do not actually know the size of the biggest storm the sun is capable of producing. The instrumental record covers only a few decades closely, the historical record a few centuries loosely, and across so short a span, the rarest and most violent events may simply not have happened yet for us to see. Two lines of evidence suggest the ceiling is far higher than anything in living memory. When telescopes turned to survey hundreds of thousands of other stars, much like the sun, they caught some of them producing superflares, eruptions hundreds or thousands of times stronger than the largest flare we have ever recorded from our own star, raising the question of whether the sun, too, has that in it, and our own sun has left a confession in the trees. Locked in the growth rings of ancient wood are sudden spikes of a radioactive form of carbon, created when a flood of solar particles strikes the upper atmosphere, and two such spikes, one laid down around the year 774, and another near the year 993. Record particle storms far larger than anything in the age of instruments, monster events that would dwarf the Carrington storm itself. The radioactive carbon is made when solar particles slam into the upper air, and a tree breathing that air seals the record into the single ring it grows that year, so the spikes can be dated to a precise 12-month. The same events leave a matching trace in the layers of polar ice, confirming them from the opposite end of the Earth. Two independent archives, wood and ice, agree that the sun loosed something colossal in those years. Discovered only recently by a researcher reading the carbon in tree rings, these events prove that the sun has fired far harder than we have ever caught it doing, within the span of recorded human history, at times when no one alive understood what had passed over them. We simply were not watching with instruments when the sun was at its worst. It is a sobering correction to any sense that the Carrington event marks the ceiling. Carrington saw the largest storm in the brief window we happened to be watching closely. It was never proven to be the largest the sun can make. Put the two walls together and the shape of our predicament is clear. We have built, in a single lifetime, a watch over the sun of extraordinary reach and precision, capable of warning a grid, hardening a satellite, and sending a crew to shelter. And yet we cannot say when the sun will fire, and we cannot say how hard it can hit. The warning, for all its sophistication, begins only at the moment the sun decides to act, never before. The whole vast apparatus is, by its nature, an answer to a question the sun alone gets to ask, on its own schedule, with a force whose upper limit we have not yet seen. The near miss of 2012 and the spikes in the ancient rings are two halves of the same warning about the warning. The worst is real. It is coming eventually, and we will not get to choose the day. That is not a counsel of despair, and it has not been received as one. If the trigger cannot yet be predicted, then the obvious response is to go and look at it more closely than ever before, to fly instruments into the very place where the field breaks and the cloud is born, and to read the sun from angles the earthbound fleet can never reach. The limits we have run into are not being accepted. They are being besieged by a new generation of spacecraft flying closer to the sun than anything before them, in the hope of one day learning to read not merely that a flare has happened, but that one is about to. The boldest of that new generation has done something that would have sounded like fantasy in Carrington's day. It has flown into the sun's atmosphere itself. A spacecraft now loops in toward the sun on a long series of ever closer passes, diving through the outer corona and out again, protected by a shield of carbon built to face temperatures of well over 1,000 degrees, while the instruments behind it stay near the comfort of a sunlit room. It samples the corona from the inside, in the very place where the wind is born and the field reconnects, gathering measurements no remote telescope could ever take, and it has flown close enough that we may fairly say a human-made object has at last touched the sun. To reach that place, it has had to become the fastest object human beings have ever built, whipping around the sun at speeds of hundreds of thousands of kilometers an hour, drawn closer on each orbit by carefully judged passes near Venus. On its deepest dives, it has crossed the boundary where the sun's atmosphere properly ends and the solar wind begins, flying for hours below that frontier and sending back the first measurements ever taken from inside the corona. Among them, the discovery that the young solar wind is full of sudden, sharp reversals in its magnetic field whose origin is still being puzzled out. Among its tasks is the old riddle met earlier, the question of why the corona burns so much hotter than the surface beneath it, a puzzle it is finally addressing, not from 150 million kilometers away, but from within. There is a quiet justice in the name it carries. The craft is named for Eugene Parker, the physicist met earlier, whose mathematics of reconnection and whose prediction of the solar wind reshaped the whole subject. When he first argued, at the end of the 1950s, that the sun must be blowing a continuous wind of particles out across the solar system, the idea was met with scorn. The prevailing view held that the space between the planets was essentially empty, and his paper was very nearly rejected outright. He turned out to be entirely right, joining the long line of those who read the sun correctly before their colleagues were ready to believe them. He was the first living person to have a spacecraft named in his honor, and he lived to sit and watch it launch, an old man seeing a machine bearing his name set off toward the star he had spent his life trying to explain. He died not long after, but the probe flies on, carrying his name into the corona he taught us to understand. A second new traveler takes a different and equally unprecedented route. Rather than diving inward, it is climbing, slowly, pass by pass, out of the flat plane in which the planets orbit and in which every previous solar observatory has been confined. From that rising vantage, it is beginning to look down on the sun's poles, regions no eye and no instrument had ever properly seen, hidden from us by the simple geometry of living in the sun's equatorial plane. The poles matter because it is there that the great magnetic field reorganizes itself between cycles, there that the 11-year rhythm is set and the polarity reverses, the deep machinery of the whole storm-making engine. It carries both kinds of instrument at once, cameras to photograph the sun and detectors to taste the wind streaming past it, so that it can watch a feature take shape on the surface, and then, as that same stream of particles reaches the spacecraft, measure directly what the surface had sent. On its closer passes, it has returned some of the most detailed images of the sun ever made, and as its orbit tilts higher year by year, it is delivering the first true portraits of the polar regions, filling in the one part of the sun that every earlier mission had been forced to leave blank. To watch the poles at last is to look directly at the source of the clock, and it may tell us, in time, something about why one cycle rages and another stays mild. What all of this is ultimately for is the closing of the last gap, the one the previous reflections laid bare. We can detect a flare. The ambition now is to predict one. We can see an active region wind tight and call it dangerous. The hope is to read its field finely enough and understand the trigger deeply enough to say not merely that it might break, but that it is about to. The effort increasingly leans on teaching computers to recognize, in the vast flood of solar images and magnetic maps, the subtle patterns that tend to run ahead of an eruption. In the hope of wringing a few hours of genuine forecast out of data the human eye cannot fully parse. It is the same path ordinary weather forecasting walked over the past century, from folklore to observation to physical models to the steadily improving predictions we now take for granted. The forecasting of space weather is simply earlier on that road. No one claims to be there yet, and it is possible that a perfect prediction of the moment of the break will always lie just beyond reach, written in instabilities too small to catch. But the distance already traveled should caution anyone against declaring a limit permanent. We have gone, within a few human lifetimes, from a man who watched a flash through a telescope and had no word for it, to machines flying through the sun's own atmosphere and over its hidden poles. The warning that was once an accident no one could read has become a science, and the science is still moving. That movement has consequences well beyond the laboratory. Severe space weather now appears on the formal risk registers of major governments, listed soberly alongside pandemics, floods, and the other rare disasters with the power to disrupt a whole society, and plans are drawn for how a country might keep its lights and its networks alive through a great storm. The threat that Carrington could only sketch in a notebook is now something nations deliberately prepare for. It is worth pausing, at the end, on the people, because it is the people who carry the whole of it from beginning to end. There is a single unbroken line running from Carrington at his screen in 1859, through Schwabe patiently counting his spots, Hale reading the magnetism in a sunspot's light, Birkeland building a glowing model of the aurora in a vacuum chamber, the spectroscopists who decoded the corona's impossible heat, the forecasters who sit through the night watching the X-ray trace climb, the aurora chasers who photograph a ribbon of light no one has named, and the engineers who fly a probe into the fire. Every one of them is doing the same thing the first of them did, looking carefully at the sun and trying to read what it is saying. Each inherited a little more understanding than the one before, and added a little more in turn, so that the reading of the sun is not the achievement of any single mind but a relay, run across many lifetimes, the baton a steadily growing fluency in a language written in light. The message has been arriving since long before there were eyes to receive it, pouring down on this planet across the whole of its history, and only in the last sliver of that time have we begun, slowly and collectively and across generations, to understand a word of it, which brings the whole account back to where it began, to the light falling on your own skin. The sunlight reaching you as you take this in is 8 minutes old, the same 8-minute-old light those very first words described. On almost every day in the history of the world, that light has carried the same untroubled message. Nothing has happened. The star is calm. All is well. The entire effort traced here, the centuries of patient looking, the fleet of watching spacecraft, the probes flung into the corona, comes down to learning to read that message faithfully enough that on the rare day it carries something else. On the day the light arrives bright with X-rays and trailing a wall of matter behind it, we will know in time to act. That is the whole of it. A star that has been speaking to us in light since before we existed, and a species that has finally, lately, begun to learn the language. If you enjoyed this exploration of one of the deepest unsolved questions in modern science, a like or a subscribe helps us continue making them. We live beside a star, close enough to feel its warmth and far enough to survive its temper, and every day it sends us the same quiet sentence written in light, 8 minutes ahead of anything it might be carrying behind. For almost all of our history, the sentence arrived and went unread, mistaken for omens, blamed on spirits, felt as a shiver in a compass and never understood. Now we can read most of it, and we are flying into the fire to learn the rest, so that the next time the sun says something other than all is well, the 8 minutes of warning will be 8 minutes we know how to use. The universe still has plenty left to reveal, and we will be following it as it does.